Welcome to the first of who knows how many lectures on Chapter 6's coverage of the reactions of alkynes. Now, for students who are actually in my class right now, I bet you're probably thinking, why in the world did Mike skip Chapter 5 and vault straight from Chapter 4 to Chapter 6? Well, the answer is because I think that Chapter 5 and the subject that it addresses were very significantly misplaced by the author of our textbook. Personally, I prefer to talk about the reactions of alkynes, Chapter 6's coverage, immediately after talking about the reactions of alkenes. It, to me, just makes logical sense. Hence, I'm completely bypassing Chapter 5 for the time being, but we'll get back to it according to our schedule later on. After today's lecture, you should be able to do the following. Name alkynes using the IUPAC naming system. Identify the hybridization of atoms in alkynes and explain in terms of atomic and molecular orbitals what that actually means. And correctly draw the mechanisms and predict the products formed when HX is added to an alkyne, halogens, or X2, are added to alkynes, and halogens and water are added to alkynes. And lastly, be able to explain keto-enol tautomerism. Before we get started, however, I want to show you something really cool. In North American culture, at least, we frequently hear people talk about contraception by using the phrase, the pill. What in the world is the pill? Well, as it turns out, the pill is actually comprised of two different compounds, ethynyl estradiol, whose structure is shown right here, and norethynadril, whose structure is shown here. You'll note that each of these compounds are actually derivations of the molecules shown over here, estradiol and progesterone. Parenthetically, ethynyl estradiol, which is once again a derivative of estrogen, has a carbon-carbon triple bond right here at this position. In other words, it's an alkyne. This molecule itself is an orally bioactive estrogen used in many formulations of oral contraception pills. Progesterone is added to the pill because of major concerns that exist about ethynyl estradiol being added in concentrated form and having some connection to endometrial cancer. Okay, well, I realize that isn't extremely uplifting, but at the very least you can see that alkynes, carbon-carbon triple bonds, are or can be functionally useful. One thing I want to point out is that in the names of each of these two compounds, ethynyl estradiol and norethynadril, you'll notice that there's a YN in their names. That YN derives from the term alkyne. Now I want to teach you how to name alkynes. Similar to the pattern we followed in naming alkenes back in Chapter 4, when you want to name an alkyne, you begin by naming the parent chain. And what in the world is the parent chain? Well, assuming that you don't have any functional groups that are higher priority than the carbon-carbon triple bond, the parent chain is the longest carbon chain that contains the triple bond. We find that chain, and then we name the compound using the suffix YNE in the place of the suffix ANE. So if we had an alkyne version of ethane, we would call it ethyne. If we had an alkyne version of propane, we would call it propyne, and so forth and so on. Next, we number the carbon atoms in the chain. Now, of course, we're going to number in the direction that gives the triple bond the lowest number, assuming that there are no other functional groups in the alkyne that have higher priority. And lastly, we write the full name, placing the substituents at the beginning of the name and the parent chain name at the end. And one quick thing I want to tell you that's sort of just parenthetical, but nevertheless very important. Alkynes that have a hydrogen coming off of the triple bond are called terminal alkynes, while alkynes that don't are called internal alkynes. Which leads us to some wonderful lecture questions. What is the IUPAC name for the following alkyne? And give the systematic name of the compound shown here. Now, the alkynyl question I'm going to let you do on your own, because I think that you have the ability to do it. I do want to focus on this one, because you'll notice this is not an alkyne. However, our chapter does mention it briefly. This is actually a compound that has two alkenes in it. How in the world do we name a compound that has two alkenes in it? Well, we call it a diene. Now, you'll notice this is a 7-membered cyclic compound that contains two alkenes. Hence, it is called a cycloheptadiene. I'll let you insert the numbers as well as the names of the substituents onto that name on your own. We now return to the subject that we've addressed numerous times, orbital hybridization. Now for the next little bit, I'm going to show you a clip that you've seen already that comes from one of my earlier YouTube videos discussing the subject. The reason that I'm doing so isn't to continually bore you with this topic. It's because I want to remind you of something that you should have learned already, with the specific purpose of focusing on how this topic relates to alkynes. In other words, I want you to pay attention to what the hybridization is of carbons that are triple bonded to other carbons. And I want you to pay attention to three-dimensionally what is actually happening with those carbon atoms' orbitals as they hybridize to be able to form the triple bond. That said, here's the clip. I'll now readdress this ever-forgettable topic of atomic hybridization. Now there are two different ways of learning hybridization, the easy way and the hard way. I, of course, prefer the easy way for everything. But on this topic, to be quite honest, you really have to learn both in order to understand what's going on. So I'm going to teach them both to you. First, we'll talk about the easy way. If I'm ever asked to determine an atom's hybridization, all I do is count how many things are around that atom. You can see me giving you this table right here. Now, the number of things around an atom, I should say, refers to how many other atoms or lone pairs are around them. So when I say a thing, I'm talking about another atom or a lone pair. So we count how many things there are, and then we memorize this chart. 2 things is an sp hybridized center, 3 things sp2, and 4 is sp3. And that should get us deep enough to be able to answer any of the types of questions that you'd encounter on a standardized exam in this subject. Let's see if we can look at some examples. What is the hybridization of each of the indicated atoms? Let's start at this one. See this carbon? We're going to count how many things are around it. By things, I mean atoms or lone pairs. This carbon has a hydrogen, a hydrogen, a hydrogen, a hydrogen. I'll hold up that. I count to 4. There's 4 hydrogens. So what's its hybridization? It's sp3. 1, 2, 3. sp3. Let's look at the hybridization of this carbon atom. How many things are around it? I've got a hydrogen, and an oxygen. Now this is one of those things that some students get confused about. They think that because there's a double bond here, I'm going to count that somehow as more than one thing. You do not. All we do is count how many things are around it. A hydrogen, and an oxygen. The hybridization of that is sp2. Let's see if we can figure out the hybridization of this oxygen. How many things are around it? It's got a carbon down here, lone pairs over here, and lone pairs over there. sp2. See that? What's the hybridization of this carbon atom? Once again, we count how many things are around it. We don't care that there's a triple bond or a double bond or a quadruple bond or a sextuple bond. That is irrelevant. We just look and count how many things are around it. 1 hydrogen to the left and a carbon to the right. There's only 2, so it is sp. Does that make sense? This is the easy way to determine an atom's hybridization. Now, as I indicated before, I am going to teach you the hard way. But before I get to that, I want to also re-solidify in your minds what we've taught before about atomic bond angles. I want you to tell me, what are the indicated bond angles? In this molecule that we decided has an sp3 hybridized carbon in the center, what is the bond angle between all of these hydrogens in this tetrahedral structure? You should have remembered it is 109.5. What about right here? This carbon only has 3 things around it in a trigonal plane structure. What's the bond angle? It's 120. And the bond angle right here, this carbon is in a nice straight line. It's 180. Thus we can see that an sp3 hybridized carbon will try to get its 4 groups to be around 109.5. An sp2 hybridized carbon will try to get its groups to be 120. And an sp hybridized carbon will try to get its groups to be around 180. It's not always dead on those numbers, but it tries as best as it can to match them. Now to the hard way, which is my way of saying now I'm going to actually teach you what's really going on I'll of course be talking about orbitals, which is a subject that often makes people poop their pants with fear. Please don't do that, because I don't think anyone would appreciate cleaning up the mess. To simplify things, I want you guys to imagine that orbitals are really nothing more than a region of space that electrons can occupy. Orbitals are in essence just empty parking places for electrons to go into. Different orbitals, of course, have different shapes. S orbitals are shaped like spheres, and p orbitals are shaped like cute little dumbbells. Now, as you should have learned back in general chemistry, every element has its own electron configuration, which is a subject that I won't review here. Carbon's electron configuration, of course, is 1s2, 2s2, 2p2. Now, carbon's valence orbitals are the ones that have the highest number, this 2s orbital and this 2p orbital. You count up the number of electrons occupying those, it adds up to 1, 2, 3, 4. So that means that carbon has 4 total valence electrons. Now let's see if we can assemble a carbon atom one layer at a time. We'll imagine that carbon's nucleus looks like this. This is where its neutrons and protons are located. This nucleus is surrounded by a 1s orbital. Now if you look up here, you see how it says there are 2 electrons that occupy that 1s orbital? There they are. These are core electrons. Now outside this layer we see a slightly larger 2s orbital. Over here in the electron configuration it says there are 2 electrons that occupy that 2s orbital. There they are. Now these are 2 of carbon's valence electrons. Outside of this layer, we see carbon's 3 individual 2p orbitals, which straddle the x, y, and z axes 90 degrees apart from each other. Now each of carbon's if we look over here, you'll see that the electron configuration indicates that there are 2 electrons in carbon's 2p orbitals. Where do those go? They go right here and right here. The third 2p dumbbell right here remains unoccupied. So let's pretend that carbon wants to bond with 4 separate hydrogen atoms to form methane, the molecule shown here. Now once again, you'll remember that the bond angle in this tetrahedral structure is 109.5 degrees. So here come our 4 individual hydrogen atoms, ready to bond with carbon. In order to form a bond, each of these hydrogen atoms, which has an individual 1s orbital filled with a single electron, has to overlap with carbon's valence orbitals somehow, so that their joint electrons can be shared in those molecular orbitals. Now look at this. How in the world are these hydrogen atoms going to be able to overlap with carbon's 2p and 2s orbitals? Where could they go? Well, we could imagine this hydrogen atom right here might be able to overlap with the bottom of this p orbital. Okay. And this hydrogen atom over here could potentially overlap with this p orbital, and this hydrogen atom could overlap with this p orbital. But if it did that, now all 3 of these hydrogen atoms have overlapped with 3 of these p orbitals. What's left for this poor hydrogen atom over here? Where can he go? Well, the only thing he could overlap with is the 2s orbital, which is kind of a little bit located, squished in here in the interior. So he'd have to kind of squish down in there. And that might create some real problems for him to be able to fit into that hole. There's another problem here too. Each of these p orbitals are located 90 degrees apart, not 109.5. So even if these 3 hydrogen atoms did latch on and overlap with these p orbitals, they're not going to be 109.5 apart. They're going to be 90 degrees apart. And then this hydrogen atom is going to have to somehow squish down so that it can fit into this 2s orbital here. This whole situation stinks, much like methane gas itself. So what in the world can carbon do? What carbon does is it takes its 3 2p orbitals, shown here, and its 1 2s orbital, and it combines them. So if you could imagine that these 4 different orbitals, the 3 2p orbitals and this 1 2s orbital. If these were all made out of molding clay and I took them in my hands and squished them all together, and then I took all of that molding clay and separated it out equally into 4 separate orbitals that are all equal size and shape, that's essentially what carbon's doing. It's taking these 3 individual 2p orbitals, this 1 2s orbital, squishing them together, and separating them out into 4 separate and equal sp3 orbitals. Carbon now places each of these new sp3 orbitals together in this kind of 3-dimensional form. And guess what the bond angle is between them? 109.5. Carbon can put its 4 valence electrons in each in one of these 4 sp3 orbitals. Now what can happen? Well, now each of these 4 hydrogen atoms can come right in there, 109.5 degrees apart, overlap with these 4 sp3 orbitals, and form a nice, beautiful molecule of methane. Isn't that pretty? That's what orbital hybridization is. The word hybrid comes from a Latin root that essentially means mixing or combining. So what it's doing is it's taking an s orbital and some number of p orbitals and squishing them together to make new orbitals. Does that make sense? Well, let's see if we can figure out and apply it to a different kind of hybridization. As you might remember, the hybridization of this carbon is sp2, and the bond angle should be about 120 degrees. So what does that mean? Well, it means that carbon has combined its 2s orbital and only 2 of its 2p orbitals together in this hybridization. Let's see if we can take a look at that. So carbon's taken 2 of its 2p orbitals and its 1 2s orbital, squished them together, and then made 3 individual equal sp2 orbitals like that. These 3 individual sp2 orbitals are then laid down in a trigonal planar structure like this. This is supposed to be all in a plane with a beautiful 120 degree angle separating each of these lobes. Now you'll notice when we contrast this pattern with what we saw in the previous slide that carbon in this case left 1 of its 2p orbitals out. It only used up 2 of these in this hybridization process. So what happened to the third 2p orbital? Where is it? It's right here. It goes above and below the plane of these 3 individual sp2 orbitals, 90 degrees perpendicular to that plane. That's what an sp2 hybridized carbon center looks like. Our carbon atom is now hybridized and ready to go. It places its 4 valence electrons, 3 individually, into its 3 sp2 orbitals, and 1 into its perpendicular 2p orbital, which was left unused in the hybridization. Now oxygen, which is also sp2 hybridized in this molecule, comes in. Oxygen has 6 valence electrons, which occupies orbitals like this. These 2 electrons, which are coupled here in one of these sp2 hybridized orbitals, as well as these, represent these lone pairs dangling off of the oxygen like so. Now oxygen comes in, and these 2 atoms overlap to form this. This bond between oxygen and carbon here in the center is a sigma bond. This perpendicular overlapping bond between the unused 2p orbitals in both atoms is called a pi bond. Now I don't want you to be confused here. A pi bond kind of looks like 2 bonds. There's a line on top and a line on bottom. Don't think of that as 2 bonds. That is 1 pi bond. It is a pi bond, or a bond formed by unused 2p orbitals overlapping. It is not as strong as a sigma bond. Now at this juncture, the hydrogens can come in, overlap with these orbitals in the carbon atom, and form this molecule that we have right here. Now let's do the same process for an sp hybridized molecule, which has a 180 degree bond angle right here. The fact that these carbon atoms are sp hybridized implies that they've used up one of their s orbital and one of their p's, and they've left the other two p's unused in the hybridization. So let's take a look at that. We've taken one of our two p orbitals, one of our two s orbitals, and we only have one, combine them to form two sp orbitals. When these sp orbitals are thrown together on the carbon atom, they form a nice 180-degree angle linearly like this. So what in the world happens here? Well, the unused 2p orbitals go perpendicular to the plane, 90 degrees apart from each other. So once again, let's go back. This carbon atom used one of its 2p orbitals. The other two 2p orbitals remain unused, being perpendicular to each other and to the plane, which is occupied by these two individual sp orbitals. So what occurs next? Well, here are my two carbon atoms, both sp hybridized, with their remaining unused 2p orbitals lying perpendicular to each other, as shown here. At this point, they fill their orbitals with their respective valence electrons. They then overlap like so. Now this bond between the carbon and the other carbon is a sigma bond. These perpendicular overlapping bonds are each separate pi bonds. Once again, this circuit here is one pi bond, and this circuit here is a second pi bond. That represents the triple bond. These hydrogen atoms can now come in, overlap with these lobes dangling off of the end, ultimately making this molecule. So as stated, in order to form a carbon-carbon triple bond, each carbon atom has to take its 2s orbital and one of its 2p orbitals and combine them together to form two separate and individual sp orbitals. sp orbitals straddle the nucleus of each carbon atom, having a 180-degree bond angle, thereby allowing hydrogen or other atoms to overlap and form sigma bonds on the side. The bond between the two carbons that forms the sigma bond in the carbon-carbon triple bond is also assembled when the two carbon atoms' sp orbitals overlap. Now the remaining pi bonds are able to be formed as each of the carbon's remaining 2p orbitals overlap. One of these, for example, could be this carbon's 2px orbital overlapping with this carbon's 2px orbital, while this one could be the 2py orbital on this carbon, and the other one could be the 2py orbital on that carbon. As they overlap, they form what kind of looks like a circular track that represents one pi bond. Here's a purple pi bond, here's a blue pi bond, and you'll note that they are 90 degrees perpendicular to each other, while the sigma bond in the middle is formed by the carbon's sp orbitals overlapping. Now, without overemphasizing the obvious, you should understand that each triple bond is comprised of a single sigma bond and two pi bonds.